Hi, I'm Dr. Jim Zoval, a professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. Let's start by talking about metabolic pathways and some strategies used in metabolism. This is kind of a summary of chapter 15. We had a chapter on each of these types of molecules that we metabolize to get energy out of. So these series of chemical reactions are metabolic pathways. 3 types. Linear. In a linear metabolic pathway, you have a series of reactions where the product of one reaction is the reactant for the next reaction, and so on. A gets converted to B, gets converted to C. Finally, you have the end product. Our glycolysis was an example of that. Circular pathways. In a circular pathway, the final product is also the reactant for the first reaction. A gets converted to B, which gets converted to C, which gets converted to D, and D is one of the reactants in the first reaction. And finally, a spiral metabolic pathway, a series of reactions used to build up or break down molecules a small section at a time. For these reactions to occur, every reaction in that pathway has to be spontaneous. If it's not, then it doesn't happen. Now, some of those reactions, if we didn't couple it to another reaction, would not be spontaneous. I want to talk about this metabolic strategy of coupled reactions. In a coupled reaction, a process that's energetically unfavorable, that requires energy, right? Delta G is positive. That doesn't happen on its own. The key is to couple that to another reaction that gives off enough energy to drive the non-spontaneous reaction. We call spontaneous something that occurs, non-spontaneous something that doesn't. So all steps have to be spontaneous for these metabolic pathways to occur. Here's our definition of coupled reaction. A spontaneous reaction provides energy needed by a non-spontaneous reaction. The example I want to give you is the formation of ATP from ADP and a phosphate. This chemical reaction is often written like this with abbreviations. ADP plus, instead of drawing the formula for the phosphate, it's usually see PI. That means an inorganic phosphate. We'll go to ATP. If we think about the energy for this reaction, here's energy, and we call that the free energy, G. And we have the energy of the reactant, ADP plus the phosphate has a lower energy. ATP has a higher energy. Going from low energy to high energy is not spontaneous. But we know we do this. That's how we make ATP. We do this by coupling this reaction to other reactions that give off energy, that provide enough energy to convert these reactants into products. For this reaction, ADP plus a phosphate to go to ATP, the change in energy is 7.3 kilocalories per mole. That means for every mole of ADP, it takes 7.3 kilocalories of energy to convert that to ATP. That's this difference in energy here. Not going to happen on its own. What nature does is couples that with a reaction that gives off energy. Here's a reaction that occurs in glycolysis. This is the last reaction in glycolysis, phosphoenol pyruvate going to pyruvate. Notice in this reaction, you break a phosphate bond. This reaction is spontaneous. Look, the change in energy is negative. The reactants are higher energy than the products. It's spontaneous to go from high energy reactants to low energy products. So the metabolic strategy would be this. Combine these two processes. This ADP that's going to get a phosphate in the top reaction, instead of getting the phosphate from a phosphate ion that might be diffusing around in the solution, get this phosphate from this molecule when it reacts. So this phosphate is transferred to the ADP to get ATP. When the phosphate comes off, phosphoenolpyruvate, you have pyruvate. So we do this reaction, and we call it a coupled reaction. Phosphoenolpyruvate, the phosphate comes off, goes on to ADP to form ATP. Notice this reaction, the coupled reaction, is now spontaneous. Delta G is negative. How do you know what delta G is? When you couple two reactions, you just add up these energies. Positive 7.3 plus negative 14.8 gives you negative 7.5. In biochemistry books and organic chemistry books, sometimes this is written like this. These two things are the same. Notice the phosphoenolpyruvate plus the ADP, we made a coupled reaction. Coupled reactions are often written like this. There's the phosphoenolpyruvate plus ADP. The phosphate goes on to the ADP to make ATP, and you have the pyruvate. These two things mean the same thing. That's coupled reactions. How is this reaction done in a biological system? It involves an enzyme. Kinases are enzymes that involve the transfer of a phosphate group. The phosphoenolpyruvate will sit in the active site of the enzyme. The ADP sits in the active site of the enzyme. The enzyme changes its shape, lowers the energy of activation, so it catalyzes the reaction. This bond to the phosphate's broken, a new bond here to ADP is made. The reactants are converted into products. The products are no longer the same shape as the reactants, so they don't fit in the active site as well, so they come out, leaving the enzyme free to catalyze another reaction. We get energy from eating food. We do that by metabolic pathways. One of those for glucose is glycolysis. We get energy out of glycolysis. Here's one way that we get ATP from glycolysis. There's some other strategies that are important in understanding metabolism. When we break down our food molecules, those are oxidation reactions. Usually oxidation reactions are spontaneous. They occur. Now, you have to have something that's going to accept those electrons. And so you have to have a reduction. It's usually the energy from the oxidation that drives the reduction. You're coupling an oxidation and a reduction together. Much like we talked about coupled reactions for energy. What happens when we oxidize the food molecules is they release energy. If we just burned it like we did wood in a campfire, it's not very efficient. We don't couple that to anything. We just warm up the universe, right? We don't do any work. In metabolism, we do these oxidations very slowly, one reaction after another, and couple those to either making ATP or reducing a coenzyme. And we'll see later in the chapter how we get energy out of the reduced coenzymes. Many metabolic reactions are oxidation or reduction reactions. Oxidation always needs to be coupled with a reduction. I told you that when we metabolize food, we're oxidizing it. Remember, oxidation either adds oxygen or removes hydrogen. So this would be an example. Say you have a food molecule here, and you're going to do a biochemical reaction to oxidize it. You couple that to a reduction. You'll start with the oxidized form of a coenzyme, and you'll reduce it. Those hydrogens get transferred from the oxidized form of the coenzyme to the reduced form of the coenzyme. For example, here's the oxidized form of NAD. If you do an oxidation of a food molecule, you'll reduce NAD, you'll change it to NADH. We'll also see that with FAD in this chapter. Sometimes we want to do reductions in biochemistry. How do we do a reduction? We have to couple that with an oxidation. And it's a good way to recycle these coenzymes. When we want to do a reduction, we'll couple that to an oxidation. We'll start with the reduced form of the coenzyme, like NADH, and we'll oxidize it. We'll convert it into NAD. As an example, NAD and NADH. Let's kind of keep track of what's going on there. As an oxidizing agent, NAD will remove hydrogen from a molecule. It'll remove hydrogen and the bond, and 2 electrons with it. As a reducing agent, NADH will provide hydrogen to the molecule. This hydrogen will come off and it will come with 2 electrons will go with it. This is what we know from the past. If we take an organic molecule, when we do oxidation, we're either adding oxygens or removing hydrogens. That's oxidation. Look at the end. At the end, by doing oxidation, you go from an organic molecule to its most oxidized form as CO2. Just like in combustion, when we burn something, we make CO2 and H2O. And going the other way is reduction. And that usually requires energy. That's what plants do. They go from CO2 to glucose. I want to show you how that happens, why we call it oxidation and reduction. I've mentioned this before in another chapter. The reduction is when you gain an electron. Very often in biochemical systems, that reduction comes from adding a hydride ion. This is a hydrogen with a negative charge. It has an extra electron. That's why it has the negative charge. So you're gaining an electron. Here is an example in this direction. We're starting with the oxidized form of NAD. We're going to reduce NAD. So oxidized form, reduced form. What happens? Look right here and here. Here's where that hydrogen adds. Here there's 1 hydrogen, here there's 2. This hydrogen comes in, those 2 electrons form a covalent bond. That's what we see here. When that happens, these 2 electrons move over here and the double bond goes to here. When that happens, these 2 electrons move on to the nitrogen and exist as a lone pair on the nitrogen. And notice the arrows go both ways. If we want to drive an oxidation, right, we need to do a reduction. We do this. We want to drive a reduction, we need to do an oxidation, we go this way. Hi, I'm Dr. Jim Zoval. If you like this video and you'd like to get the entire course or just some of the chapters on video, I have the entire course and video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.